All right, so our last section on vectors is 5.6, and it's vectors in space. Space just means we're not on a flat plane anymore. We're on a 3D surface. Okay, so that's what a 3D coordinate grid looks like. Kind of weird. Your XY plane is at the bottom. That's where we were originally. The z-axis is coming up off the bottom. Okay. So because 3D is quite a bit harder to draw, we're not going to be doing things visually like we did in 2D. Connecting the end to the beginning and drawing a diagonal. It would work. It works just fine. But it's rather tough to draw 3D stuff on a 2D board. Okay, so we'll be sticking mostly with formulas and numbers and stuff like that. Okay. But the important thing I want you to know from this picture is that the third axis is called the z-axis. Okay, it's the z-axis. And the way you can figure out which way the z-axis points, our book calls it, let's see, I think they call it the right-hand rule. All right, if you're, let's see, it says your index finger, have that point in the direction of x. They have your middle finger point in the direction of y, and then your thumb will point in the direction of z. Right? So they're all perpendicular to each other, x, y, and z. They're all perpendicular. So let's say, x was down and y was at the door, z would be towards the back wall. Okay? Makes it very easy to figure out if you just use your right hand. Okay? Not your left hand. If you use your left hand, then your thumb points the opposite way. Okay, so it's right hand. Right, so just what I'll do a lot of times is I'll put up the formula we used to have, and then I'm going to ask, how would we extend it to 3D? Okay, so in 2D, we did this the very first day of class. Distance formula. x2 minus x1 squared plus y2 minus y1 squared. Add them up. Take the square root. Well, in 3D, we got to add one more part onto that. Okay, our coordinate has an x value, a y value, and if it was 2D, we'd stop right there. That's x and y. Now we have to add on the z value. Okay, I want to see if we can figure out what our distance formula is in 3D. Okay, based on the kind of the pattern we got right there. Anybody think they can guess what's going to be added on to the end? Yeah, z2 minus z1 squared. That's it. You got to add on that part to the end. So you still have x2 minus x1 squared, y2 minus y1 squared. Just add z2 minus z1 squared. For every formula we look at today, the extension into 3D is pretty much going to be that simple. Just taking almost what you did in 2D, one more step. Right, so let's try an example. So let's find the distance between the points -1, 3, 2. So again, this is x, y, and z. And P2, that's my x2, y2, z2. Okay, I didn't really mention this, but that formula that I just showed you, it's the Pythagorean Theorem. It's just the Pythagorean Theorem in 3D. That's all. So let's find our distance. Okay, first thing I'd do, just put down your square root. And then write down everything that needs to be filled in. And then fill it all in. All right, let's start with x2. Emily, what's x2?
4.
Yep, 4. Shelby, x1?
-1.
-1. Right, next is y2. Amy, y2. -2. And then y1, Sam?
-1. No, 3.
3, yep. 3. Naisha, lastly, how about z2? Four is x1, so we already used that. So 5, and what about z1? 2. Okay, let's go back through, make sure we got it. So we had 4 minus -1. Yep, that's good. We got -2 minus 3. That looks good. We got 5 take away 2. That looks good. All right, let's do it up. Andrew, what's 4 minus -1? 5, and then square it? 25. Okay, Max, what's -2 minus 3? And then square it? 25 again. And Paige, 5 minus 2? 3, and square it? 9. So you get 25 plus 25, that's 59. Just like always, if you get a square root, you can reduce. I'll expect on the test you're going to reduce it. So if you had something like this, I'd want to see that. Square root of 20 would be like 2 square root of 5. 59, can't do anything with that. So that's good. Okay. Any question on distance in 3D? All right, so this is not vector stuff right here. This is just, here's a coordinate, here's another one. Find how far apart they are. That's all that was. All right. So now the rest of it, we'll look at our vector formulas. All right, so in 2D, right, we had a unit vector I that represented pointing 1 unit right. We had a unit vector j that represented pointing 1 unit up. But in 3D, if we just use I and j, we're stuck. We're stuck here. I and j would never let you get off the bottom of that plane. Okay? We're going to have a third letter that's going to be another unit vector. And it's going to be a unit vector that points on the z-axis, 1 unit up. Anyone have a guess which letter we're going to use for that? Yeah. K. So now an example of a vector in 3D, it might be 2i minus 5j plus 6k. That last component, that's for the z-axis. If you wanted to write it with our algebraic notation instead of ijk, use your angle brackets, and it's a, comma b, comma c. On the test, you might see either notation, unit vector or algebraic. Okay, so remember, A, B, and C, those are your components. A is the component on the x-axis, B is the component on the y-axis, and C is the component on the z-axis. These kind of vectors are a little bit more useful in 3D. If a plane was really flying, you might have to take into account it's not only heading maybe north and west at the same time, but it's also changing altitude. Maybe it's descending. So that can complicate it a little bit. Right? We didn't look at anything in 3D with that, but you could, and that's more realistic. Okay. Just like in 2D, if you have a vector that has an initial point at the origin, that's a position vector. No change in that definition from what we already had in our notes back on Monday. So if your vector's got an initial point at the origin, that's a position vector. Okay, any questions so far? Okay, so in 2D, that was our formula to find a position vector in 2D. Take x2 minus x1 and y2 minus y1. The order you subtract them in, that is important. It's always terminal minus initial. If you accidentally switch the order, it wouldn't affect the magnitude, but it would affect the what of the vector.
Position vector.
Well, what are the two things that describe a vector? It has a magnitude and speed, that's magnitude. Distance, that's not really something we represent with the vector. The direction, no. All right? If you switch the order, you subtract these, you're going to get the wrong direction. Okay, Kyle, how do you think I'm going to represent my initial point in 3D? So it was x1 comma y1 in 2D, but what do we need to add? Yeah, x1, y1, just add z1. Same idea with the terminal point. x2, y2, and now z2. And now let's figure out how would you find a position vector in 3D. Okay, Sean, what do you think I'm going to have to add onto my formula in 2D to make it 3D?
You're gonna have to add like add a z2 minus z1.
Yep, exactly. So now you've got x2 minus x1, y2 minus y1. Just add on z2 minus z1. In fact, if I was making a reference sheet, I would just put all the formulas on in 3D rather than copying them in 2D and 3D, because if you put them in 3D, just block out the last part, and then that's the 2D version. Just pretend like the z's are 0. They don't exist. All right, so let's find a position vector for P1 and P2. Let's just fill in what we have to fill in. Okay, Yadira, what's the first number that's going to go right there?
4.
Yep, 4. And Tom, second number? 4 minus? So 4 was x2, what's x1? -1, yep. All right, so we'll do that in a second. How about Ethan? What's going to come next?
Is it 2 minus 6?
All right, so we're looking for y2. Looking for y2.
6 minus 2.
6 minus, well, 4 is an x value. So we don't want 4. 6 minus, what'd you say?
2.
2, yeah, 6 minus 2, good. All right, and then the last one, Brandon, what's that?
2 minus 3.
2 minus 3. Okay, so our position vector, 4 minus -1 is 5, 6 minus 2 is 4, 2 minus 3 is -1. Okay, how would you write that with I, J, and K? Just in case they asked us to do it that way. Yep, 5i. Yep, go ahead. Plus 4j. Okay. Yep, minus 1k or just minus k. Same thing. Okay, any question on finding a position vector in 3D? So guys, just make sure you use that formula right there. All right, so we're going to look at all the formulas that we looked at, how to add, how to do a scalar product. They're all pretty much going to be the same. We're just going to add a z component to all of them. So if you want to add two vectors together, add the x components, add the y components, now you have to add the z components. If you want to subtract two vectors, subtract the x's, subtract the y's, subtract the z's. Okay, I used the symbol plus or minus, so I didn't have to write the whole thing twice. Bless you. Okay, the next one is a scalar product. When you multiply a number by a vector. What property do you use there? It's very similar to a basic property. When you're trying to scale a vector, you got to scale each individual component. So we use the distributive. Yeah, it's like the distributive property. Multiply the number in front of the vector to every component. So alpha times the x component, alpha times the y component, alpha times z. Okay, and our magnitude. Well, that's what we had in 2D. I said to you to square each component, add them up, and take the square root. In fact, I can use the same description in 3D. Square each component, add them up, and take the square root.
Wait, what's that second one?
Alpha times y.
Yeah, what does that mean?
That's a scalar. That's a scalar product. So that would make a vector longer, shorter, or it could change the direction.
Is that y1?
Yep, y1. Okay, what would you have to add on to this to find your distance in 3D? z1 squared, yeah. So to find the magnitude of a vector, square each component, add them up, and take the square root. Same formulas we had all week.
What's that one?
That's the magnitude of a vector. Okay, any questions on those formulas? Okay, the notation is the same. If something is written as a vector, it should either be written as a bold letter, or you can write it as a letter with an arrow over it. Okay, let's try that. All right, so vector v, it's 2i plus 3j minus 2k. Vector w is 3i minus 4j plus 5k. And the first thing they want is to add them together. Find v plus w. So the way you add them is just combine. It's almost like combining like terms. Combine your I components, combine your J's, combine your K's. All right, Ashley, can you tell me what do I get when I combine just the I components together?
5.
Yep, 5i. Okay, Olivia, how about the J's?
-1.
Yep. Negative 1j or just negative j. And Adam, how about the k's? 3k. That's it. That's the only way we're going to add vectors in 3D. We're not going to do it visually. Just going to do it like that. I will ask you on the test to do it visually in 2D. Okay, just like we did. Okay, that symbol, somebody remind me, what's that symbol mean again? That's the magnitude. So in other words, I want to know how long. What's the first symbol? Anytime you want to find magnitude, you should always write this symbol down so you don't forget to do it. Square root, yeah. Put down a big square root. Okay, and our formula says square each component, add them up and take the square root. Right, so Ben, if I square my I component, what do I get? 4. Paige, if I square my J component, 9. And lastly, square the K component, Brandon,
4.
4 again. Let's add that up. 4 and 4 gives me 8. 8 and 9 gives me 17. And that's it. That's the length of that vector. Square root 17. Okay, and C is asking us to find 3W. What's that called? Is this a dot product? We're multiplying? No. We are multiplying. It's a scalar product. Okay, it's just taking a number times a vector. That's not a vector times a vector yet. Okay, how about Josh? What's the 3 going to do to W?
You're multiplying?
Yeah, so visually, like if you drew it out, what would be the difference between W and 3W?
Oh, it's going to expand it.
Yeah, how much? 3
times.
Yeah. It's going to make it 3 times as longer. Okay. So, we got W. As Josh just said, you multiply the 3 out to each part. So we're going to get 9i minus 12j plus 15k. That's it. That's a scalar product in 3D. Great. Any questions on that? As I said, it probably feels a lot like review today because it's all the same stuff, just adding in one small step. All right, so now let's look at dot product. Okay, it's not going to be any surprise here. The way you would expect the dot product in 3D to work, it's exactly like 2D, except you got to extend it to 3D. All right, so in 2D, this is what we did yesterday. You multiplied your x's, plus you multiplied your y's. What's the extra step we're going to have to do today? Multiply the z's, yep. So product of the x's plus product of the y's plus product of the z's. Let's try to find that dot product in 3D. In fact, why don't you try that on your own? Take 60 seconds, see if you can figure out what the dot product is. And the dot product is going to be used to do the same thing we did yesterday. Eventually, we're going to find the angle. We're going to find the angle same way we did yesterday. Okay. Give that a try. All right, so Shelby, first 2 numbers I multiply to find dot product. 5 and 2. So 5 plus 2. 5 times 2 plus, Amy, next 2 numbers. Negative 3 times 3. Good. And last 2 numbers, Tom. Negative 1 and 6. So we weren't consistent in the order that we wrote down the products. That's okay because it is commutative. So 5 times 2 Somebody started with the bottom and went to the top. So we should do it the same way all the way through. 5 times 2, 3 times negative 3, and negative 1 times 6. It's going to come out the same either way. Okay, we learned that earlier. Okay, so we get 10 minus 9 minus 6. And Owen, when I simplify that, what do you get? Negative 5, yeah. Negative 5. Great. Any question on that? So that's your dot product. So without even getting into the angle yet, if I asked you, are these two vectors perpendicular? Based on what you learned in 2D, what do you think? Would they be perpendicular? No. If they came out to a dot product of 0, then they would be. Same rule.
Still works in 3D.
Yep, still works in 3D. That the formula to find an angle in 3D is identical. There's no change. Cosine of your angle is the dot product divided by the product of the magnitudes. The only change in the formula is how you do a dot product in 3D. There's one extra step. Okay, we already went over that. How you find the length in 3D. There's one extra step, and we already went over that. Okay, but it's the same formula. Okay, so I'm going to take, I think I used the same two vectors I had up above. 2i minus 3j plus 6k. Yep. And 5i plus 3j minus k. Yep. And I want to find the angle between them. Okay, I used the same vectors because we already did some of the work. We already got the dot product. Okay. That came out to, what was the dot product? Negative 5. So we already got that. Now we're going to find the length of u and length of phi. All right, so length of u, square each component, add them up, take the square root. How about Max? What's going to be my first number? 2, and what do you do with it?
No, you add it.
Well, before you are going to add it to something, but you have to take the 2 and you got to do something with it. Square it. Okay, so 2 squared. Next part is negative 3 squared. Ashley?
9.
9. And Zach, my last number? 36. Good. Okay, so we add all that up, and what do we get? We're going to get a nice answer here.
49.
Get the square root of 49, which is 7. Yep. So we get a nice answer for square root v. I'm sorry, square root of, yeah, for u. Now we're going to do v. So it's going to be 25 plus 9 plus 1. 5 squared, 3 squared, negative 1 squared. Yep. 9 and 1 is 10, and 25 is 35. Okay, so I got all 3 pieces of information I need to find the angle. Cosine theta, dot product over the product of the magnitudes. Okay, so if I just wanted to know the cosine of theta, well, it's right there. You just type that in. But I don't want the cosine of it. I want theta. So how am I going to get rid of cosine? Inverse. Take the inverse cosine of what's on the left and on the right. Okay, you do have to be careful when you type it in. Put your denominator in parentheses, otherwise order of operations isn't done correctly. So 7 square root 35. close the parenthesis for your denominator and for your function. Okay. So the vectors are close to perpendicular, not quite, 96.9 degrees. And that's an angle in space, in 3D, 96.9. Okay. Any question on that? All right. All right, so last thing, I'm not going to go through the entire section. I just want to mention what I already did yesterday. Okay, the cross product is a different way to multiply two vectors. I'm not going to show you how to do it. So that's why if somebody said to you, I'd like you to multiply vector v times w, you have to ask them how. Dot product or cross product. Okay, we didn't study cross product in 2D because you can't. It doesn't apply to 2D. Cross product only works in 3D. And there's applications to a lot of stuff in geometry and physics. When you find a cross product, the answer is a vector. You don't get a number. When you do a dot product, you get a number. That number is useful if you want to find the angle, sure. But when you do a cross product, you get a new vector. What you end up with is if you have two vectors and you do a cross product, it gives you a third vector that's perpendicular to both of the other two. Okay, so why would you want to know that? Well, let's say you knew where your horizon was in a plane. Okay? If you had two vectors that represented ground, you could automatically calculate which way is up. Or you could also calculate which way is down. Right? So if you're in a plane and visually it was at night and you lost your orientation, you're kind of confused, your instruments could figure out, as long as they know two vectors that represent ground, they can find which way is up. So that's kind of a simple use for a cross product. And another kind of interesting thing about the cross product is it's not commutative. If you switch the order, it comes out different. You'd find up instead of down or down instead of up. So that could be a big problem in a plane if you want to go up and you accidentally go down. All right, but that's all I'm really going to say about cross product. Any other questions about cross product? Calculation is simple, but we're not going to get into it in this class. All right. So for tonight, you don't have to worry about cross product. Just on 363, we'll take a look at 15, 17, 29 to 35 odd, and 41, 43, and 51. This is a pretty good review for everything we did all week. Okay, if you can do all those, you should be okay for the test tomorrow on vectors.